Recursion is fundamental to the idea of computation, and is so general that you'll have most likely already seen it, but under different names. So the goals of this video are to understand that recursion generalizes loops, and that recursion and induction are really two ways of looking at the same thing. And lastly, that recursion is actually a really simple way to express some complex ideas. If you've seen the movie Inception, you're familiar with the idea of nesting something inside of something. To solve a problem in the world you're in, you go into the dreams of the person you're interested in, fix it in the dreams, wake up and do whatever it is you wanted to do. However, instead of dreams, we'll be looking at solving a big problem by first fixing a smaller part of it, and then dealing with the rest. Let's start off with an example most people will be familiar with. Here, induction and recursion aren't even necessary. They're more like a cute, different way of looking at the same thing. Imagine somebody asks you to sum up the numbers from 1 to n. This can be written as the sum from I equals 1 up to n of I is equal to 1 plus 2 plus and so on up till n, which we know is the same as n times n plus 1 over 2. So you use that last equation, do the calculation really quickly, and ta-da, the person is really impressed that you could sum up all those numbers in your head that quickly. But then say the same person asks you to sum up all the numbers from 1 to n plus 1. Even though you could do the whole multiply and divide by 2 trick, again, it's probably easier to just add n plus 1 to your previous answer. And then by doing so, you stumble across a new way of looking at the problem. That is, the sum from I equals 1 to n plus 1 of I is the same as 1 plus 2 plus so on up till n plus 1, which is the same as n plus 1 plus the sum from I equals 1 to n of I. It's still the same problem, but you've found a new way of looking at it. It's called recursive because in order to solve the sum at n plus 1, you need to have solved the sum at n. However, there's one really important thing to understand about this view. The n at the top of the sigma is smaller than the n plus 1 that you started with. It's still the same problem, but on the right we assume we've already solved it for the smaller number n. We don't really care how we've solved it, be it with the trick or just doing the sum, only that it's right. Imagine if somebody gave you a 5-layer series of Matryoshka dolls, and then asks you to make a 6-layered one. Are you going to put in the effort of making all 6 layers? No, the easy thing to do would be to make a big outer one that can fit all the ones that you were already given, and call it a day. Let's hold that thought for a second and talk about induction. If you don't already know, mathematical induction is a powerful way to prove properties about natural numbers. A property is any statement which is either true or false. Some examples are is either even or odd, or is divisible by 7. Sometimes we give properties names to save us some writing. If we decide P is the property for is either even or odd, we then say P of 43 to say 43 is even or odd. If we decide Q is the property for is divisible by 7, then Q of 49 is how we say 49 is divisible by 7. If we want to say a property doesn't hold, we write a funny looking dash. So the funny looking dash, Q, of 45 means 45 is not divisible by 7. From now, I'll just use P as a stand-in for any property. Mathematical induction says if you want to prove P about all natural numbers n, it's enough to show that P of 0, meaning P is true for the number 0, and if P of n for some random, or more correctly, arbitrary, because random has a very specific meaning in maths, n, then we can probably use that to help us show P of n plus 1. P of 0 is called the base case, and the bit where we use the answer for P of n to show P of n plus 1 is called the inductive step. 0 doesn't have to be the base case. Sometimes it won't even make sense to consider it. So the base case can be any number, although in general we use 0. You might not have seen the equation, the sum from I equals 1 to n of I is equal to n times n plus 1 over 2 before, but say you want to check it, convince yourself that it's true. We can use induction to do so. Here, since we start the count from 1, we can use n equals 1 as the base case. But you can easily generalize it to 0 if you wanted it to. So the left is just the sum 1 on its own, and on the right, you just plug in n equals 1 to see that 1 times 1 plus 1 all over 2 is 1 as well. If that felt too easy, that's not a problem. Usually the base case is that way. The inductive step is to assume that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. Now we consider the sum from I equals 1 to n plus 1 of I. Is it the same as n plus 1 times n plus 1 plus 1 all over 2? That's what we're aiming for. Usually the trick at this stage is to figure out how we can use this assumption. If there's inequality, we have to figure out how to break the current problem down so that one of its parts looks like the left or the right. But we've seen this bigger sum before. From the recursive definition of the sum, we know it's the same as 1 plus 2 all the way up to n plus 1 is the same as n plus 1 plus the sum from I equals 1 to n of I. Now we see the left bit that we recognize. So let's try using this assumption of equality. We can substitute in to get n plus 1 plus n times n plus 1 all over 2. We can pull out the factor of a half to get half times 2 of n plus 1 plus n of n plus 1. We can again pull out the factor of n plus 1 to get n plus 1 over 2 times all of 2 plus n, which we can simplify to match the goal of n plus 1 times n plus 1 plus 1 all over 2. If it feels a little bit like cheating, that's understandable. You're somehow proving something by assuming it. But the thing you have to remember about that is that you're proving something bigger by assuming it works for something smaller, and then figuring out how to use that smaller case to prove the bigger one. And we know we can't keep getting smaller and smaller because of our base case. In this case, we stop getting smaller at the number 1. Try it for yourself. Start at n plus 1 times n plus 1 plus 1 all over 2. Split it up to find the n times n plus 1 over 2 inside it. Replace that with the sum from I equals 1 to n of I. then show what's left is the same as the sum from I equals 1 to n plus 1 of I. So induction is starting small with the base case and then working up to a bigger case. Recursion is just a different way of looking at the same thing, starting with a big thing, then figuring out how to split it up until we have a smaller version of the same problem, until we get to something really easy. Direct computation is rare, and it can be difficult to figure out. Induction and recursion work because there's a base case. With induction, it's that there's a place to start. And with recursion, it's a guarantee that we don't keep falling down the rabbit hole forever, and we eventually hit the ground. When there isn't a base case, we can run into problems. First, it becomes difficult to think about because infinity is not very intuitive. In more practical programming terms, it leads to non-termination, your program never stopping. That might seem like a small issue, but it underpins the halting problem and the foundations of theoretical computer science. So to get around this, computer scientists generalize this idea of smaller, so it applies to more than just numbers and call it well-founded induction, which really just means making sure that recursion doesn't break your brain or your computer. It's a big enough problem that most languages just kind of ignore it, but Idris tries really hard to keep it under control. Here are some different ways of expressing a problem using the inductive, the recursive, and the direct views. Take the sum from I equals 1 to n of I. We can say inductively it just looks like starting from 1 and then adding up all the numbers until we reach n. Recursively, we can say the sum from I equals 1 to n is the same as n plus the sum from I equals 1 to n minus 1 of I. And the sum of n equals 1 is just 1. The direct view would just be saying n times n plus 1 all over 2 is the result that you're looking for. Take another example called the factorial. Inductively, you might say it's starting from 1 and then instead of adding, you multiply all the way up till n. So 1 times 2 times so on up till n. Recursively, however, it's defined as n factorial is n times n minus 1 factorial, with 0 factorial being defined as 1. But there isn't really a direct calculation for n factorial. We have Stirling's approximation, which for those of you who are interested is root of 2 pi n times n divided by e all to the power of n. Lastly, let's have a look at the Fibonacci sequence of numbers. Inductively, we would say they are 1, 1, 2, 3, and to get the next number, you just add the previous 2. Recursively, however, we would say f of n is equal to f of n minus 1 plus f of n minus 2, saying that f of 0 is equal to f of 1 is equal to 1. Notice here that we have 2 base cases, which is fine. And the direct view of computing the nth Fibonacci number is to define x as 1 plus root 5 all over 2, y as 1 minus root 5 all over 2, and say f of n is equal to x to the power of n minus y to the power of n all over 2. And the representation or the view that you choose depends on the context that you're working in. In the early days of computing, some processors didn't support multiplication in hardware, so they couldn't use the direct approach. In some embedded devices, floating point multiplication, division, square roots, and powers are really expensive or aren't available, and for smaller quantities it would just be easier and more space and power efficient to calculate Fibonacci inductively. The examples I gave above are notorious in Introduction to Recursion examples everywhere, but when there are inductive or direct ways of calculating something, students and readers are often left wondering why on earth someone would express it in a more complicated way recursively. The problem with the above examples is that they're essentially linear. You can start at the base case and just work your way up to the answer without making any choices along the way. And so choices are a great place to show your first example of non-linearity, and a recursive view makes it easier to wrap your head around the problem. Mathematicians called nk, surrounded by brackets, n choose k, and write it to stand for how many ways you can choose k things from a bag of n things. We can think about this inductively too. The base case is n equals 0, or the empty bag. Choosing k from n only makes sense if k is smaller than n. So, how many ways of choosing nothing are there from an empty bag? The answer is just one, doing nothing. If that seems strange, don't worry. Empty bags and choosing nothing take a bit of getting used to, but are perfectly valid things to do. So we have 1 as the base case. Then there's a bag with one thing inside of it. Let's draw it here, a circle with a dot inside of it to show one thing. There's one way of choosing nothing, so we're left with nothing in our bag, and one way of choosing one thing from it, so we're left with one thing. For a bag with two things inside it, there's one way of choosing nothing, two ways of choosing one thing, so we can take either the blue or the orange, and one way of choosing two things from it. We can take both. And likewise for a bag of three things in it, there's one way of choosing nothing, three ways of choosing one thing, so we can take either the blue dot or the orange dot or the red dot. There's three ways of choosing two things. That's the same thing as leaving one thing behind. So we can take red and blue to leave behind orange, we can take orange and blue to leave behind red, or we take orange and red to leave behind blue. And lastly, there's only one way of choosing three things, or everything from the bag. We can write this out inductively, but in a table. So have n choose k, where k is representing the columns, and n for each row. We start off with 0 choose 0 is 1, then 1 choose 0 is 1, and 1 choose 1 is also 1. The next row we have 1, 2, 1, and in the row following that we have 1, 3, 3, 1. For those of you in the know, you'll have seen this before, and it's called Pascal's triangle. You might have spotted a pattern, how the previous row influences the next one. You simply add the number above the number you want, and the number above and to the left of the number you want, to get the number that you need. This technique of building the table up row by row gets unmanageable pretty quickly. There is also a direct way of looking at the problem. N choose k is equal to n factorial, all divided by k factorial, times n minus k factorial. And if you think about it the right way, in terms of permutations, the n factorial at the top, but ignoring the order of the k things you took out, the k factorial at the bottom, and ignoring how the rest of the things that you left are ordered, the n minus k factorial, it makes some sense. But here, a recursive way of thinking brings clarity to the situation. Imagine you have to pick 4 things from 20, like randomly selecting a team of 4 people from a group of 20 people. How many teams of 4 are possible? You could try writing out the triangle until you hit 20, but you might end up wasting a lot of effort on parts of the triangle you won't need. Or you could try breaking it down recursively. For that recursion to work, something needs to get smaller. Either the 4, or the 20, or both. Like choosing 3 from 19, or choosing 4 from 19, or even choosing 3 from 20. Let's think about each of these. What would you have to do to change the problem into something that looks like choosing 3 from 19? And that's easy. You pick a person, you like them, and you keep them in your team, and you keep going, but now you want to choose 3 people from the 19 that you have left. What about choosing 4 people from a group of 19? It's the same. You pick someone from the group, but you don't really like them, so you reject them, and you don't consider them again, and you keep going, but this time you have to figure out which 4 people you want from a smaller group of 19. But there's not really a good way of thinking about 3 from 20. You've just changed the problem. It's like picking a person, putting them in the team, and then putting them back to consider for later. So is the answer just 19 choose 3 plus 19 choose 4? Yes. But we're not quite done yet. We can't just keep subtracting 1 forever. Eventually, either your team will be full, or the team won't be full, but there won't be enough people to choose from. These are our base cases, and we have to check for them every single time we recurse into the smaller problem. When the team's full, the number on the bottom will be 0, and we know that there's only one thing to do: do nothing. For the other case, we can say that whenever you get to 4 choose 4, replace it with 1 and call it a day. And this means we can avoid having to figure out what 3 choose 4 and 3 choose 3 mean. Because we're just counting how many ways, this is fine. But if we were coming up with a list of all possible teams of 4, then we'd have to pay a little more attention to this case and realize that 3 choose 4 actually means this problem can't be solved, and figure out how to deal with that. Looking ahead, practical examples of recursion can be found in compilers, sorting algorithms, the fast Fourier transform, graphs, mazes, and databases, and a bunch of other scenarios. In nonlinear cases like these, for or while loops on their own, which are good for linear computations, aren't very good at expressing the problem concisely. You end up needing to keep track of the recursion manually, either with a stack or a queue, depending on what the problem at hand is and how you're solving it. In the last video, we talked about examples like the syntax tree for nested noun phrases like swim in rivers in Scotland, or for arithmetic expressions like number plus number plus number plus number. For the case of arithmetic expressions, we can write a digit is one of 0 up to 9. A number is either a digit or a digit followed by a number. And an arithmetic expression is either a number or the sum of 2 arithmetic expressions. If that notation ever confuses you, and you start thinking about what's to stop you from going on forever, or why is this the same thing on both sides of the arrow, then you take a deep breath and just think about the things we've been talking about. The things on the right have to be smaller than the things on the left. So for arithmetic expressions, we could have a number subscripted by n, saying it's either a digit 1 or a digit followed by a number n-1. Here the n, the 1, encodes the length of the number in terms of how many digits it has. Similarly, we can say an arithmetic expression can be subscripted by k, where it's either a number of length n, or it's an arithmetic expression of k1 plus an arithmetic expression of k2, where k1 and k2 both need to be less than k. In fact, we can even say k is equal to the maximum of k1 and k2 plus 1. And that way, we're counting the height of the syntax tree. Pause the video and draw it out to convince yourself of that. Then, for every single arithmetic expression ever, regardless of the size, you say it's a big union over all the ones of size k from 0 to infinity. And for the sentences, you can just make NP1 and NP2 the same and you'll get the same effect. Go check it for yourself. Here, recursion is going from big to small, starting at the top of the syntax tree and working down, whereas induction would be starting at the bottom of the tree and working your way up, meeting and combining with others. The thing that made it click for me is that it doesn't matter where the top of the tree is. It can be anywhere. All we want is that the next level down, the recursive step, bottoms out and does the work, at which point we recombine it and say that we're done. Even in a for loop, there's a counter and there's a limit, and the thing getting smaller, there is the difference between the two. We will get to infinite recursion and handling non-termination eventually. But until then, all you need to remember is this key thing, that recursion and induction are basically the same thing. They're two ways of looking at the same concept. And they consist of a base case plus an inductive step.